All right, good. Okay, so my name is Brian Healy, and I'm a postdoc at University of Minnesota working with Professor Michael Coughlin. And on behalf of him and his group, I'll be talking about our research today. So I'll start out just by listing the postdocs, grad students, and postbac who are part of the group. And in addition to everyone on this list, I also encourage you to stay tuned for talks by Alec, Gunny, and Erik Moreno, because there's a lot of synergy between the Coughlin group and Erik's group at MIT. So in order to avoid too much repetition, I'll be talking more about the electromagnetic part of multi-messenger astronomy and ZTF, and they'll be talking more about the gravitational wave side of things. All right, so I'll first start out with just a little intro to time domain astronomy. So I feel like oftentimes you might think of astronomy as having a lot of things that don't change much over time. They're around for billions of years, but there's also a lot going on much shorter timescales, a lot of changes happening, many astronomical objects that show brightness variations on short timescales of months, days, hours, and even less. And so these break down into two major categories, persistent variables and transients. So variables they're changing and they continue to change. We see them, you can look up and point to them night after night, year after year, and they'll be continuing to vary. Transients, we see the brightness change once, and then they kind of drop off the map. We don't see that happen again. And so to study both variables and transients, and in turn, time domain astronomy at scale, we need an observatory that provides a wide field of view, a short observation cadence, because these things are changing very rapidly, and then sensitivity to faint sources, so we can see as much of what's out there as we can. So enter the Zwicky Transient Facility, or ZTF. So this is a northern sky survey located at the Palomar Observatory in California. It achieves these characteristics I just mentioned. It has a wide field of view, a fast survey rate, and it observes faint sources in multiple colors. And it provides full sky coverage of its available sky every 2 days. And in a recent data release, DR16, it has output about 4.6 billion light curves. So I just want to show a little bit of example ZTF data to introduce you to what we're working with. So these are light curves. They're plots of a source's brightness on the y-axis over time on the x-axis. On the left-hand side, I have a light curve for an astrophysical source. It happens to be a binary system that's eclipsing. And on the right-hand side, I have an image artifact caused by just a blend of two nearby sources. So one of these, like I said, is astrophysical, one is an artifact. We want to tell the difference between these and many other kinds of sources. We want to classify all these different light curves that we have from ZTF. And so just to motivate that a little bit more, so obviously this benefits just anyone who's interested in variable sources. If we have a whole bunch of classifications we can put on light curves, then they can use those for ensemble studies. But more near and dear to the Coughlin group is for transient follow-up. So again, transients, they occur once and then they're gone. And so we're particularly interested in kilonovae, which are the mergers of stellar remnants called neutron stars. And so when these events happen, there might be variable sources near to the transient that we're interested in. And so we can classify those, then we can exclude those sources that have been known to observe past variability from when we search for the kilonova itself. Because if it's already been varying sometime, years in the past or months in the past, then it's not going to be the transient we're looking for. And then source classification also benefits anomaly detection, because we can discover new kinds of sources when we search for the anomalous outliers among the different classifications that we get for the light curves. All right, so this brings me to the ZTF source classification project, or SCOPE. So this is the code that we use to do this source classification. And so there's a QR code there that links to the repository. It's open source code, and it's Python based. We try to run things as professionally as possible. So we have a continuous integration, continuous development pipeline. We regularly update the documentation. And this is also a hackathon topic. So you'll be able to get your hands on this code later this week if you're interested. So just some details about SCOPE. It's a supervised and active learning process. So we use a training set and we build it up over time with human input. For one round of machine learning classifications, we'll have humans go through and take a look at least some subset of those. And then if they say yes on those, we actually incorporate them into the training set and continue to grow it and improve the quality in this way. We use two different taxonomies for classification. So the first is ontological, or basically the intrinsic astrophysical kinds of sources that we're interested in. But then we also have this phenomenological taxonomy as well, where we're not really worried about, in that taxonomy, the exact astrophysical nature. We just want to know what the light curve shape is telling us. And so using these two taxonomies helps us, it provides useful information for anomalous sources. If they don't fit into any of the intrinsic categories, there might be new ones we haven't discovered yet. So the phenomenology helps there. This also avoids the complications of overlapping classes between ontological and phenomenological classes. So, for example, you might have two different kinds of astrophysical sources, but they're both periodic. And so how do you, in your hierarchy, how do you, avoid too much duplication? Well, if you separate out the ontology and the phenomenology, then you can do that. So we train binary classifiers for scope. So we get independent predictions for each class rather than using like a multi-class classifier. So this supports having multiple labels per source of varying specificity. So you might have a very general one that says it's variable. You might also have a very specific one that says it's some specific kind of source. So running binary classifiers helps to assign these multiple sources, multiple classifications per source. And it's also flexible to adding new labels. So if we have classification probabilities in the past, then we change our hierarchy. We don't need to worry as much about how the previous classifications need to be reinterpreted when we've added new labels. So the algorithms we actually use are two of them, a convolutional neural network and XGBoost. And so that brings me to the features that we actually use for these two algorithms. So we don't just put in the light curve data itself, because it's oftentimes very, you can see there are gaps in the data here. There's different sampling rates. There's that almost line over on the right that is sampled at a different rate. So we don't want the algorithms to latch onto any of those as the thing that it'll use to assign classification. So instead, we kind of boil down that information into a combination of summary statistics and these 26 by 26 little images of magnitude time histograms, which I'll get into in a little bit. So to generate features, that's actually the most computationally intensive part of the whole process, and specifically period finding of these light curves. So just to run a Lomskargel periodogram on a single light curve takes about 1 second per light curve just on my laptop's CPU. But of course, we have of order 10 to the 9 light curves, so every second really counts. So we run GPU accelerated versions of these algorithms on a high performance compute cluster, STSC Expanse, to reduce that time by about an order of magnitude. And we take advantage of the GPU having thousands of cores and being very good at parallel processing compared to the CPU. And so I said I was going to talk a little bit more about these image features that we include. So we have these magnitude time histograms called DMDT. And what we actually do is we map changes in magnitude, or basically the brightness or that y-axis on the light curve, and changes in time on the x-axis to 26 bins. And so by doing that, we create a standardized image, so to speak, as an additional feature that then we feed into the convolutional part of our neural network. We don't use this for XGBoost. And this improves classifier performance over just using the summary statistics. And here I just have two examples of what these DMDT histograms look like for two different kinds of astrophysical sources, and how you might start to pick out differences between them if you use this. So the architecture of our neural network is over here on the right. And so it's got two kind of prongs to it. So most of the features, just those summary statistics, pass through fully connected layers where it says features in the green circle. And then the DMDT histograms are input to the convolutional branch of the neural network, which is up at the very top. So then, of course, we have dropout layers in between our dense layers to avoid overfitting. And then we end up getting just one number per source per classifier, which is the classification probability just for this binary. Each binary classifier provides this for each label. So just a few details on neural network training. So we have about 80,000 sources in the training set. Since there are multiple colors per source, this translates to about 180,000 light curves. We train right now 44 binary classifiers. And I plot over here on the right the area under the ROC curve as a function of the training epoch for each of the classifiers. And so right now, we've been casting a broad net on what classifiers we train, but some are very well represented, some of the labels, but some are very highly imbalanced. There might only be, say, 50 or so positive examples in this sea of 80,000 sources. So that's kind of tricky to get the classifiers to train on. I'm interested in what solutions might be able to be offered by the hackathon later this week, but we're in the process of figuring out which classifiers are going to be really the ones that are worth sticking with and which don't have enough data right now. So just a little bit about XGBoost. So this is a different kind of algorithm. It combines individual decision trees sequentially, and in the process minimizes underfitting of the data. And so one of the nice things about XGBoost is that it lets you know feature importance, whereas it's tougher, more expensive to do that with DNN, the neural network. We get these plots for every classifier in XGBoost that tells us the feature importance, and so we can then learn which of our features are most relevant for classification, and it achieves similar or better performance versus the DNN. All right, so the current status of scope. So we have generated DR16 features for ZTF for 20 fields using SDSC expanse GPUs. And we've obtained classifications from both the neural network and XGBoost algorithms. We've also trained models we're using our trained models to run on sources that are near transient candidates to assist with follow-up decisions when we get a multi-messenger event. So again, if we know what's around, what kind of variable sources are near a transient, then that's always helpful to follow up most efficiently. And we've got a paper in prep for scope to report the methods and classifications we get. And this will include a catalog of tens of millions of variable source classifications to be made public for further use. Okay, that brings me to the next effort on the electromagnetic ZTF kind of side of things in our group. And that's this next repository called Nuclear Multi-Messenger Astronomy, or NMMA. And again, another QR code here. You'll see that there are a lot of the very similar, we maintain this repository in a very similar way to scope. And so this is a Pythonic library for probing nuclear physics and cosmology with multi-messenger analysis. So it's a pipeline for Bayesian analysis of gravitational wave and electromagnetic data. It includes models of a bunch of different kinds of transients, including kilonovae, like I mentioned before, as well as gamma ray bursts and supernovae, et cetera. The workflow is generally to train models on simulated data, then download those when needed, because those models get very large, and then sample from the priors of the parameters we're interested in to then fit the observations we have, and then determine the event parameters for that specific transient. And we can use cluster resources to run this better at scale. So here's just what that looks like, running NMMA to fit kilonova light curves. So we only have we've only observed one kilonova up to this point. It was in 2017. This is what it looks like in a bunch of different colors. Again, we've got basically the brightness on the y-axis, and then time. It's in time and days on the x-axis, and it's a little bit cut off. But it's just a few days here. It's like 2, 4, 6, 8, basically, for those tick marks. So this is decaying. It decays relatively rapidly, and then the observation points are in the colors, and then we fit a model to each of those. So just a little bit more about training these models. So again, we don't have a whole bunch of observational data to work with, so we have grids of simulated light curves that are associated with the physical parameters that produce them. And so we want some continuous mapping, though, between the parameters and the light curves. We don't want to just be stuck on the grid. We want to be able to interpolate between them, too. And so what we actually do is first we map the light curves to eigenvalues using principal component analysis. And then we use either a Gaussian process or a neural network to then map between the input parameters for the transient and then those light curve eigenvalues. And so we found that, at least on the neural network side of things, using a broad few-layer neural network approximates effectively the Gaussian process in much less compute time, which I'll mention in the next few slides is very important. So this is a very similar plot, a little more cluttered, not publication ready, but just showing basically the same thing as the previous plot, that we've got the kilonova light curves. The simulated light curves are are dashed black here, and then the neural network results for when the model gets trained and it has to reproduce these light curves is in blue. So it's not perfect, but again, the runtime here is very important because all this is going to be happening very fast. We want to be able to run basically as data come in, and so we're achieving good performance with the faster algorithm here compared to the Gaussian process. And so just a little bit on the status and goals for NMMA. So the updated models are being used for analyses of past events right now. And like I said, the new TensorFlow neural network-based training runs faster than the Gaussian process that was previously in place. And so we're adding new features as needed. to the code and expanding the documentation so it's easier for more people to use it who haven't already been immersed in the code already. And so we then the goals, we want to be able to run on gravitational wave and electromagnetic data as fast as they become available. And we want to use an API service to start automated analyses. And I've got one more bullet point there that's a little bit, there we go. So, and we want to, basically the major goal here is to be able to have a paper ready for submission after an event within 48 hours after the event's been detected. So again, that kind of speaks to the speed at which this is occurring. All right, so just one more slide. I've got here from Andrew Toivonen in our group. And so he's working on something very related. So he's working on generating simulated kilonova light curves, and then from those getting some additional parameters to then offer as data products to the LIGO data release that comes out when there's a gravitational wave event. So he starts from parameter estimation from the gravitational wave event, and then runs 10 to the 4th equation of state draws and marginalizes over those, combines ejecta fits to then, and a light curve model to then yields these data products here, these kilonova light curves. Again, they're probably looking pretty familiar to you by now. And so then the goal is to have a few data products added to LIGO from that. So that would be BNS, which is binary neutron star ejecta, or NSBH, which is neutron star black hole merger ejecta, probabilities of each of those, as well as ejecta mass estimates. And then he wants to provide this at a 90% credible interval across the from the UV to the infrared AB magnitude estimates. And so this is a work in progress, but with LIGO 04 underway, it'll be important to keep pushing forward on this and hopefully get these added to the products that are released. So that's all the slides I have. So thanks for your attention, and I'll take any questions.
Thanks, Brian. Do we have any questions? I have one actually on when you were talking about VDTs versus a CNN, and you said that they had very similar performance on the XGBoost slide. Have you tried other neural network architectures? Or like what specific architecture did you test this against?
Yeah, so the specific neural network architecture is the one that's in the slide here. And so, yeah, I haven't experimented with other kinds of neural networks. I think it would be really interesting to see what maybe some kind of recurrent neural network could do, and as opposed to what we've got here. So yeah, definitely, like I said, hackathon ideas.
Yeah, so basically these are the benchmarks for that.
That's right.
Hackathon. Okay,
Yep.
That's great. Any other questions? Thanks.
So I'm wondering a little bit about the ecosystem of discovery. So you had the graph with the sources that you had like 50 examples of. And to my mind, it's sort of, you should classify into the stuff you know about. Everything else is in the classification of, oh, somebody should look at this. Does that work, or does somebody should look at this be 1 million an hour, or how does it go from never seen to seen enough to train?
Yeah, so that for our purposes, that's definitely a function of just as this training set was being built up, what sources people were focusing on. And so yeah, my understanding, this happened even before I started working on the project, but basically my understanding of it is that certain experts on different kinds of variable stars were asked to classify as many sources as until they got sick of it, and so yeah, I think it just is a matter of just that those ones that are more underrepresented were just maybe the expert that we didn't have an expert in that specific kind of source, and so yeah, that just basically would be a matter of how much kind of human time we'd want to put into really building up that training set, because you do want to start for something that's that we can trust to then get reliable classifiers. So that's kind of the challenge there.
Any other questions? If not, let's thank Brian one more time. And our next speaker will be Professor Matthew Graham, who is presenting on behalf of his own group from Caltech.
Can you hear me? Can you hear me? There we go. At some point you'll deafen. Okay, thanks. So good morning. I got asked at short notice to present for my own group because currently I am my own group. The person who should have been presenting is Naharika Sravan, who was my postdoc until a few months ago, and she's now faculty at Drexel. She, at short notice, I think, was unable to attend. So I got asked to present the work that she's been doing. So a lot of what you're going to see is actually her work. And so I know what it's about, but maybe the real technical details I'm not so clear on. So this whole area of multi-messenger astronomy, Brian gave a very nice introduction. We're particularly focused on at Caltech optimizing follow-up of transient alerts because we're running this Vicky transient facility, which I'm the project scientist for. So this is currently the best optical sky survey that's going on. Now, the Rubin Observatory is being built in Chile, which is going to be a 6.5 meter telescope, which will survey the night sky down to a very deep depth. And 7 filters over 10 years, and that'll start probably in about 2 years' time. And there's a big effort here at the University of Washington where they're trying to figure out what to do with all that stuff. It's a shame none of them are here to learn how to do it properly, but that's the way it goes. But we have a 1.5 meter, 75-year-old telescope, which is doing just as well as Rubin and laying a lot of the ground infrastructure for what Rubin will do. And Rubin is going to be about a factor of 10 larger than ZTF in terms of data volume and that sort of thing. So as Brian said, we observe as much of the northern sky as we can. We cover the whole northern sky observable from Palomar Observatory just outside San Diego every 2 nights with this wonderful camera. And DR18 just came out last week, and we have 2 monthly data releases at the moment. But the important thing is that we do this real-time observation. I mean, we do the data archiving stuff that Brian was talking about. We also have real-time data alerts. So what we do is we take a picture of the sky now, and we have a reference image, and we take one away from the other, and anything that's left over in what we call a difference image is something that's changed. It's either got brighter, it's got fainter, or there's something there now that wasn't there before. And we call that a transient. And then we send out a binary alert packet to the community saying, well, here are thumbnails of what was taken, and here's a bit of other information from the pipeline, and maybe here's some ancillary data like what's the nearest thing here and whatever. And we put out about somewhere between 500,000 to 1 million per night of those alerts, depending on whether it's the winter or the summer, because summer nights are shorter than winter nights. So we can't observe as much sky. And Rubin is going to put out about 10 million. Now, the good thing about ZTF is it's a 1.5 meter telescope. That means the things that we discover, our faintest objects, are about what we call 21st magnitude. And you need a 5 to 10 meter class telescope to do spectroscopic follow-up of a 21st magnitude transient. Rubin's going to go much deeper, and they're going to find 25th magnitude transients. And you need either a 30 meter ground-based telescope, which we don't have yet, or JWST for that, which is a very, very limited resource. Now, on planet Earth at the moment, there are 11 10 meter class telescopes, and that's the resource we have, that limited resource, to do follow-up for the things that are really interesting. Now, ZTF is great at doing discovery, but it can also be used as a follow-up telescope because it has a really wide field of view, 47 square degrees. And where that's useful is for things that LIGO is detecting, because LIGO detects gravitational mergers and then says somewhere in these 2000 square degrees of sky, the merger occurred. And there are certain types of compact object mergers that LIGO produces that we believe have an electromagnetic counterpart. And the most obvious one is when two neutron stars merge. There should be a very rapid flare. So back in August 2017, LIGO detected this first binary neutron star merger, and every piece of glass on the planet suddenly was covering the LIGO reported error volume and saying somewhere there must be an EM counterpart. Can we find it? And we found it. We haven't found one since. And that's affecting all sorts of ideas, but we think it's going. Now, LIGO 04 is now running. It started just about 6 weeks ago. They haven't found any binary neutron star mergers yet. They've had a couple of close calls. And of course, each of those close calls, everyone goes, ah, and we need to look up the sky. And this is really inefficient. Now, what happens is LIGO comes, we get an alert within minutes to hours from LIGO. That triggers, okay, we need to start tiling the LIGO localization volume, and that's going to produce alerts. Each ZTF observation produces, a single observation produces 1,000 alerts. And then we need to filter. So if you'll use, if you're taking 200 ZTF observations to cover the full LIGO localization volume, if you're lucky, you get 200,000 alerts. And then those go through various filters and filters. And then maybe we end up with still 500 things that we think may be possible kilonova EM counterparts. And then we need to collect data about those. What's the host galaxy? Do we do forced photometry? Is there more information we can do to sort of feed into that? And so that's the pipeline problem. But we have a bottleneck problem, because if we've got 500 candidates from a single night, we can't take a spectrum of each of those with every 10-meter class telescope on a planet, because there's not enough time. And there are a lot of other astronomers who will get very upset if we say, no, you can't do your observation that you've been planning to do 6 months' time, because we want to try and see if this little blip on the thing is real or not. That's not efficient. So we have limited resources, but we need to use those in the most efficient way to identify the event, but also to place constraints on the interesting light curve physics that we might be seeing in how this thing evolves with time. Because there are, as Brian was saying, there are different theoretical models of what the kilonova may be producing, which the observations may allow us to constrain, so that we can say, oh, what we're actually seeing is this particular physical situation going on. But this additional follow-up is absolutely critical. If we have one detection tonight in the optical, we need to know when is the best observation that we need to take with the resources that we have on hand for following time, so that we can constrain all these different theoretical models we have to say, oh, well, this is the most likely theoretical model to the observations that we're seeing. And the problem is that classifiers, I mean, we can run these classifiers on what we've got so far. They're really rubbish at telling us what to do next, right? And they don't adapt. Unless you retrain your classifier during the daytime on this wealth of new data you have, which is going to be very computationally expensive, you can't do that. So we need something else. We need a process that is free from fatigue and from bias, because I tell you, postdocs and grad students get really tired if they're going through all these thumbnails going, that's real, that's not real, that's real, that's not, I don't know, my eyes have blurred so far. We need something that's low latency, different from the type of low latency that other tiers in A3D3 are considering, but still for in terms of astronomical resources, this is fast work, this is low latency, and it needs to be scalable up to the sort of Rubens thing. So 04, as I said, started a few weeks ago. It's operating at twice the sensitivity, or it will eventually. They've got some problems with the Virgo detector. Everything is not so good as we had hoped initially. But what we're going to get in 04 versus 03 is we're going to get even more detections of binary neutron stars. Localizations won't improve. What that means is we're going to have far more candidates, however, in terms of what we're looking at. So we really need some way of doing it. And so the current system just doesn't work. The other problem is that we're not investing in follow-up resources in the same way as we are in detection. So we're already, vastly increasing our detection rate rather than what we can do with follow-up. So there's why we need this idea of autonomous decision-making. So let's see what we got here. Right. So this is the sort of thing we get from LIGO. We get a localization map, which says somewhere in this, 2000 square degree region of sky, this thing has a mass gap, has a neutron star, so it's a binary detection, maybe 10 a year. And what we get from observation is, so this is a light curve, right? This is brightness versus time. So there may be some null detections, and then the LIGO event gets, and then we may get different, for different sources, we'll get different magnitudes, different measurements of how bright they are in different photometric filters. So this will be the G filter, and this will be the R filter. So this will tell us how blue it is and how red it is. And that's important because different types of objects will also have a different evolution as they're cooling down, which will give us a different color evolution over time. But then we have a limited resource on the ground. Maybe we have 30 hours per semester where we can get different follow-up, more additional thing on time. Maybe we can get one per night. Maybe we can get a low resolution spectrum, all this sort of thing. So the question is, let's say we have a 7-day window in which we can do follow-up for kilonovas because they fade really quickly. So how can we allocate all these resources optimally for this type of situation? Now, the naive strategy is that the classifier will give us, oh, this is a kilonova score. And so why don't we just rank everything in terms of that and give the full budget that we have available to us of what we can do to the most confident one? Or we could say, well, we can sort of go down the list in decreasing order and go at one here, one here, one here, one here. Or we could try and say, okay, we want to improve the classification scores. So how do we allocate that in the best way? Or maybe we want to improve the light curve constraints to say that this is the theoretical thing and we can allocate. Or maybe there are other ways of doing this. This is a hard decision, partly because the follow-up can be misallocated, right? You may make the wrong decision. And there's nothing worse than realizing you've just used up your hour of time on a 10-meter telescope, which is maybe $100,000 of observing time. And you're not going to get that back. And then you have to say to the allocation committee next time, well, we were wrong last time when we allocated it. We didn't get the good result, but please give us more time because this time we know we're going to do right? Doesn't work. I mean, so, maybe it's best overall to rule out the borderline cases, say this is clearly not one of these. We're going to use our time to limit it down. But the ideal strategy really has to be optimal over all of these and given all future outcomes. So this is where reinforcement learning comes in, or where reinforcement learning is the sort of solution that Harika has particularly been working on. So the idea here is that your reinforcement learning agent is learning through experience how, given a particular situation, it can take the action that affects returns achieved later. So formally, this is, this is formulated as a Markov decision process type thing with a sequence of states which tell you what the agent is observing in terms of the data that it's got in hand, actions, which is what will the agent decide actually to do, policy, which is the important bit from the machine learning aspect, which is the function that maps what you're currently doing to the distribution of actions that you can particularly have. And then this idea of reward, that what is the utility of taking a given action in a given state? So if I decide to observe now, how's that going to affect what my future thing is? And then I've got a score coming back on that. And so reinforcement learning considers the full distribution of outcomes at each time step that you're considering as you go forward in time, and all future actions and their outcomes and so on, and then chooses the best action right now that maximizes an overall reward at some future time. So very different from that sort of classification problem that a lot of what's going on. So what we've done is, because the real world is far too complex, we've created a toy. We wanted to demonstrate, first of all, to the astronomers that this is a solution that will work before we go, no, this is what you need to do, and just give us all your time and we'll let the machine do it for you. instead of the expert. So we have a toy system that Naharik has developed called Pythia. So this is a toy kilonova follow-up agent. So we have 9 transients we're considering, and one of them is a real kilonova. The others could be gamma ray bursts or supernova or things that masquerade or whatever. So we have 9 transient that we're following. We do follow up. We're saying that we can take 1 action a day. We can take a G observation, an R observation, or an I observation. And there's a finite window, finite horizon of 7 days. And if the kilonova gets data added to it, that's a score of 1, else it's 0. So that's our basic, simple setup. And what we want to do is maximize the number of follow-ups that go assigned to the true kilonova. So nice, simple solution. So we generate a whole suite of simulated light curves for these things, and train the system on this particular setup. Say, these are the things you want to do: assign, assign, assign. There are various decisions we make about what our policy is, what we're using to map the actions to the states and all that sort of thing. And we've taken the most simple linear model going. This is a very simple reinforcement learning model that we're just training. We've made certain decisions about the technical details of what we're doing, such that we know this thing will converge, but we want to demonstrate that even a simple model applied to this toy situation would actually work, because that's the first thing we need to do. What we find is when we run this through with time and whatever, if we were entirely random, this is where we get. So Pythia, we actually end up with something that does about 3.5 times better than random. So we actually have a model that actually works better than random, gives us a result. This proves that this is a learnable problem, which is an important thing to say to review panels, right? Now, there are various decisions that we made in the architecture that we went for and the type of the policy we went for and whatever, which we know are not good enough for the real situation. We have this idea that we've taken this linear policy model. It's probably not rich enough, and so we need to do something with a more realistic, a more complicated policy model, maybe shifting to one of these things called deep Q networks. There are other things about the action space that we're looking at. Again, it's very simplistic. There are things about the training that we've done for the input data model, where we used a CNN, but maybe we need to use a GNN. All sorts of, we know what we've done so far is not good enough for reality, but we have good ideas about what we need to be doing to move those things forward. But the important thing is that our toy model actually gives results that are better than random. The next question is, well, how does it do against humans? So what we did is we found 6 volunteers, and they also trained. They went through a test training process on the same sort of data similarly. 4 of them identified themselves as expert kilonova hunters, and 2 of them said they were non-expert. Now, overall, they all do better than the simplest reinforcement learning toy model system, given the same data, which is as to be expected, because if the toy model, if the simplest toy model does better than the experts, then we're really in trouble, because they're the ones who are making all the decisions at the moment and trying to do the science. So you hope that they don't. What's interesting, however, is that there is a body of work, or there are certain objects where the system actually does better than most of the experts, which is telling us that the reinforcement learning model is learning different things about what's going on and making different decisions already than what the experts are doing. So one of the things we were interested in is, okay, let's take a random event and see where the expert did well and where the in the sense of explainable AI, can we actually understand where the reinforcement learning model is doing better and where the human's doing better or whatever? Now, it turns out that Pythia is really bad at, because of the reward scoring that we have, that if you give 1 point for the kilonova follow-up observation being made and nothing for else, Pythia is not motivated to do exploration of bad solutions, whereas humans are. Humans like to do a bit more exploring. Well, if I put it here, what happens if I put it here? What happens if I put it here? Our current reward model for Pythia doesn't reward that sort of strategy. And so therefore, we know that it doesn't do so well in that regard. And it turns out that that sort of strategy actually works better, it seems to, for the humans. But humans also have blind spots. And there are certain types of behavior that we see where Pythia does do better and the human doesn't, because they're not so good. It turns out humans are not so good at identifying, I think it's gamma ray bursts versus kilonova versus supernova versus kilonova. So it's things like that. So there are differences which are good and which we can sort of fold into. So that's the reinforcement learning. The other thing we're interested in at Caltech is this broader issue that the reinforcement learning is good, but LSST is going to produce, as I say, 10 to the 7 alerts per night, and they have a 60-second latency on ours. On ZTF, we have about 20 minutes because we don't need it, but Ruben have sort of focused on this. So that means we may be seeing burst rate data rates of up to about 6 gigabits per second. Now, the astronomy community has 7 what are called community alert brokers that are going to be receiving that full data stream from Ruben, and they're distributed around the world. There's one in Chile, one in Germany, 3 in the US, 1 in France, 1 in the UK. The one we run at Caltech, or the one we're designing at Caltech, is called Babamore. Now, the idea here is that a lot of these are putting big computer models or big intensive computer models in place, or saying, well, we need a supercluster which is running all these models to be able to do all the classification on these alerts and interesting things. And we're saying, no, you can just do this with FastML. So what we're working on at Caltech is we take fiducial models from ZTF. So things we're already running on the ZTF alert stream, just really simple binary classification models to say, is this a real alert or is this not a real? Is this alert a detection of something real or something bogus? Something that's past all the other things, but we still think is junk. So we call that real bogus. And that's the model is called BRI and has a false percent rate of less than 1%, which is good. We have a slightly more sophisticated model which says, well, is this thing that I'm looking at, is it hosted in the sense that there's a galaxy behind it? Is it orphan? There's nothing nearby. Is it nuclear in the sense that it's right in the middle of the galaxy? Is it a variable star because there's stuff around it which suggests it's a variable star, or is it just, again, junk? So we have these 2 models. We've also got time series models that we're trying to run less. We have less dependency on these, but these are the 2 important for classifying the real-time alert stream. And so what we've been doing is we've been exploring about porting these models from the cluster to cheap commodity hardware accelerators. Because if I can run one of these things on a $100 system, then that means that anyone can plug into the alert stream and run it on their own $100 system and do what they want with it, which is great for education. So we've had a couple of people looking at, a couple of years ago, looking at edge TPUs. And the BRI model hits about 2,000 classifications a second, which means that it can do a night's worth of ZTF alerts in about 3 minutes. So it'll be able to do a night's worth of Ruben alerts in about 30 minutes. So we can beat real-time processing or real-time inferencing or classification with a $100 piece of kit rather than the $10,000 piece of kit you need in your thing. I've got a summer student this year who's now looking at trying to port these models onto FPGAs. We want to see if that's a better solution. Maybe there's more flexibility, that sort of thing. So you could imagine that, you know, you spend $1,000, you buy 10 of these things, you're running a different model in each one of them, you've got them all connected up to your Raspberry Pi, and there's your classification engine for the real-time alerts that Ruben is giving you, which would be very nice. The other thing is, you know, astronomy data is there's a lot of black in there, right? What that translates into is that we actually have very sparse data sets, particularly these thumbnails. So this is just 63 by 63 pixels. This is what goes in the ZTF alert packets and what will be in the Ruben packets. There's a lot of useless information in there. And so we don't need to be thinking about 6 gigabit per second data rates. If we can reduce that into something that's still meaningful, we can have a much lower data rate as well, which would make it much easier to share the events around to a larger community as well. Not everyone needs to be plugged into the fire hose. We can actually reduce the fire hose down to a trickle, and it's still as information rich. So one of the things we're doing is, you know, taking the alert packets and seeing if we can put them through an autoencoder in some way and using the latent space representation instead as the thing that then goes into the classifiers. And that would be a much lower data, I mean, still information rich, but a much lower data volume, which makes things easier and makes things cheaper. One of the reasons we're also interested in doing that is thinking about the next generation sky surveys. So we're beginning to think about what we might follow up with ZTF. And if we replace the CCDs that we have in our current camera with CMOS, then our data volume will go from here up to here, increased by a factor of 1,000. And we can just do 1 second imaging on the CMOS and read it out at that rate. And that's really good because there's a new bit of exploration space that we're interested in, which is what the fast optical sky looks like. And there's all sorts of stellar phenomena related to accretion disks with cataclysmic variables and X-ray binary stars and all this sort of thing, or maybe with blazars and AGN and jet physics and things that are happening very close to the event horizon that may be detectable on those sort of timescales. And when we're up here, we know from other talks you're going to hear today that we really need fast machine learning to do any science. So there's beginning to think about what sorts of things can we do, or what sorts of things might we need to have in place to be able to do this, again, for exploring the time domain. So I'll finish there. Thank you.
Thank you very much. Do we have any questions? I do have one question. Yes. I'm sorry. So you have this Pythia simulation data
Yes.
set. How well does that actually replicate the data? Do you have any uncertainty numbers on that?
How well does it replicate the data? Well, so the input into Pythia is coming from the types of simulations that Brian was talking about. So if we believe the simulations are correct, then the data looks.
Yeah, I mean, I guess my question is, how correct are the simulations?
Well, we have one observed EM counterpart to a kilonova so far.
Okay.
So, and the problem is we don't know if that's a regular. 1708-17 seems to have been a slightly unusual kilonova.
Okay.
LIGO 04, if we detect nothing, then that tells us something about kilonova and their EM counterparts. If we detect the rates we should do, then that also tells us something about. So we're in this interesting, the next 18 months are going to be really interesting to see our ideas of how kilonovas form or what their electromagnetic counterparts should be are right or not. But what we believe is what we've got at the moment. Now, one of the things what we're also interested in doing is those, you know, the Gaussian processors and the stuff that Brian was talking about is computationally expensive. And it would be nice if maybe we could put machine learning to replace that and do simulation-based inferencing. That way we could actually potentially explore a much larger parameter space in terms of what the theoretical models are producing, which then means we might have even better constraints to go into the reinforcement learning and do things that way. But again, that's you know, work to be done. Yeah.
Very interesting. Any final questions? Otherwise, let's thank Professor Graham. Our next speaker will be Alec Gunny on behalf of Erik. I'm just gonna butcher the last name, I'm sorry. Erik Katsavounidis. Katsavounidis, I'm so sorry. Should have asked beforehand. Yeah, you can, if you want, you can just put your laptop to the side, share your
That one you
screen.
were just on would be the first one. No, the other one you were just looking at. Yeah. I can go off this. And then they'll switch to them, I guess, when we transition. Oh, God. Okay. Cool.
So are you doing your own or
He's going first up here. And he's done.
you'll swap? Okay, great.
Does that work?
Yep.
Cool. Hi. Yeah. Well, as I said, my name's Alec. And I'll be sharing some work that I've been doing with my colleagues at MIT and at University of Minnesota on, we'll all be talking about some of the work we've been doing on applying machine learning to gravitational wave physics. I'm going to start off by giving just kind of sorry. I'll start off by talking about just kind of a high level overview and then some of the work we've been doing on building machine learning infrastructure to be able to do the work that we're doing, hopefully faster and better. Then they'll talk about some of the specific work itself and some of the results we're getting close to. So really quick, brief, high level overview. Gravitational waves happen when really, really large objects out there in the universe accelerate really, really quickly, and then they ripple the fabric of space-time so violently that we can detect those waves here. And what we typically measure at gravitational wave observatories are time series of this unitless quantity called strain. That's kind of the main thing that you'll need to know, is that we have 2 or 3 typically channeled time series that we're doing sort of all of our analysis on. That's not entirely true, but let's say that's true for now. And so when we want to do machine learning on this data, there are sort of a few really desirable things that we would like to have. And they kind of come from the constraints of the problem itself. So when we're training, we'll often have really, really large volumes of these time series that are typically too big to keep in memory at once. So they're going to live on disk, and we'll need to iteratively load them and then move them to the GPU. We have really, really good simulations in the gravitational wave physics space. And so it would be nice to be able to leverage those in the context of doing machine learning. And there's also a lot of kind of important signal processing operations that, have good physical priors as things we might want to use. And so being able to build those into the network, do them on the GPU, take gradients through them would also be really valuable as well. And then in inference time, there's sort of 2 different use cases. So one is offline, where we try to, let's say, validate these models on really, really large swaths of data, in which case we have to be able to pour through the data, obviously, as quickly as possible. In the online setting, the data rates maybe aren't necessarily as high, but we would like to do things at, let's say, like millisecond scale latencies. And then again, all of this data are streaming time series, but our networks tend to operate on maybe sort of fixed snapshots of these time series at a moment in time. And so if you take these snapshots at a fast enough rate, you're gonna have a lot of overlap sort of from one inference to the next. And so being able to just stream new data to the network and not have to kind of deal with this additional data IO would be really desirable. And then oftentimes working with models that have been built with different backend, maybe use different precisions. And so being able to address all of these in sort of one inference deployment would be really desirable. And so we've been building tools to kind of address the problems with sort of this sort of paradigm of how we like to build things. For time reasons, I won't get too much into it. But basically, the idea is to, as much as possible, make the cycle of having an idea, implementing it, testing it, repeating that, be as sort of frictionless and fast as possible. That way we can try as many ideas as possible and hopefully get the best ones in the deployment. So on the training end, the library we've been working on is called ML for GW, on the nose, but it's exactly what it sounds like. It's a bunch of sort of torch utilities for implementing common gravitational wave physics operations efficiently on GPU. And there'll be kind of, I'll show you where the GitHub repo is in a second, but some of our latest additions all kind of stem from this fact that we are really starting to focus on these much larger data sets that we cannot fit into memory at once. And so some of the most recent additions, I've talked about this before at some of our other meetings, some of the most recent additions, though, are building data loaders that can read from memory in a chunked fashion. So we kind of load a bunch of data up front and then iterate through it once it's in memory, and then discard it, load another one in memory asynchronously. And that way you're kind of trading off between, you know, the IO time, the amount of data that you have to keep in memory at once, and then ultimately kind of randomness comes into play into that. And then on the sort of leveraging a simulations end, we've been doing some work to start being able to generate signals, simulated signals in real time, so you can effectively have sort of unlimited training data as you go through. And you'll see kind of the impact of that in some of the work that Ethan is going to talk about, and he'll have a poster about that later as well. We only have one particular type of waveform implemented right now, but we're happy with kind of the way the infrastructure looks like, and we're excited to hopefully add more waveforms going forward. And then we have also kind of implemented new ops to be able to do kind of more robust whitening of the data. So sort of normalizing by sort of your expectation of what the noise is, getting that out of the way so that you can focus on more valuable signals. And this is kind of a brief diagram kind of showing how we leverage it in one of the projects, which again, Ethan will talk about. Don't need to go super into what the actual flow is doing, but it's how we sort of augment data to be able to train a binary black hole detection network. And in doing so, we're able to kind of really robustly leverage a lot of the things that we sort of know about the physics of what's going on, and build them very composably into these very fast data augmentation pipelines that are implemented on GPU pretty efficiently. And then on the inference end, we have a set of tools. Can't see it here, but it's called Hermes. I can see it at the bottom, I guess. And these are for leveraging what's called like the inference as a service model. So you sort of have a centralized inference server that at inference time, you really only interact with via kind of lightweight client APIs, and then the inference server itself kind of abstracts all the details of how the model is actually getting implemented for scaling it up, et cetera. So again, this is kind of, you know, we use it when we're doing sort of large scale offline inference for this binary black hole detection network. It's kind of a brief sort of flowchart of how it goes down. Again, I don't really have time to get too much into it, but you can see that we have different models that each use kind of different backends for very specific reasons. And so we're kind of expanding the number of backends we support. So in particular, TorchScript, which is sort of Torch's native serialization format we now support. And then also, so this kind of like flow of data through a set of models is in the inference as a service nomenclature called an ensemble. And so being able to represent models with specific that ensemble. So in this case, the neural network is the only thing that's going to get updated over time as we retrain the network. The other things are sort of static over time. And so being able to keep those the same, but be able to update the version on the neural network itself without interrupting service, it will be really valuable when we go into online deployment. Oh, what did I do? There we go. And so there's a couple of use cases on the left is an example of how we use it in the online setting for the deployment of a noise subtraction algorithm we call Deep Clean, where again, we find it valuable. We retrain Deep Clean, let's say every hour, and then we're able to push new versions to be into deployment or into kind of like a canary version for validation without interrupting the service, so the pipeline can sort of run continuously. And then we also used the same model in an offline fashion for for validating our binary black hole detection algorithm by holding out of a centralized inference service, which we then deploy a sort of fleet of clients to just bombard with inference requests, and we can pour through months of data pretty quickly. And again, Ethan will talk more about that. And so all of this is on our organization's GitHub repo, and most you if you're not even working gravitational physics, if anything that's sort of in the time series modeling space, we think there's probably a lot of room for collaboration there. And the more use cases we kind of get into here, I think the more robust all of the tooling around it will be, and the better off we will all be sort of for it. So if you are interested in anything like that, please come talk to me, and please feel free to check out our GitHub, because we're always looking for more collaborators.
See that?
Okay, hi everyone. My name's Ethan Marx. I'm a graduate student at MIT, and today I'll be going into a little bit more details of some of the applications that Alec was describing earlier of machine learning to data analysis problems in gravitational wave physics. So in the first section of this talk, I'll be discussing a gravitational wave event detection pipeline that we've been working on that we recently renamed to A-frame. So the benefit of machine learning in this context here is lower latencies compared with the standard match filtering pipelines that are sort of state of the art in production deployment for the LIGO collaboration. And additionally, these match filtering pipelines suffer from some problems with scalability of their template banks. So as you increase the parameter space that you're interested in searching, you have to increase the number of templates, and computationally there's a linear scaling. And this problem is easily solved with machine learning, since during the training process, we can sort of pay that cost once upfront. And sort of the philosophy that we've adopted with A-frame is to sort of provide high quality data and robust data that sort of leverages our knowledge as physicists. And to that end, we've implemented a variety of different data augmentation strategies. In this slide here, I'm describing some of the augmentations that we use to leverage larger noise data sets. So, for example, when we're constructing our training batches from background strain data, what we'll do is we'll sample kernels from each of the interferometers independently. And this sort of allows us to see a larger amount of noise instances by effectively time shifting our data compared to if you were to just sample noise instances at the same moments in time. In this middle row here, I'm describing a strategy that we've adopted where we oversample these things called glitches, which are non-Gaussian noise artifacts in the LIGO detectors. And these are sort of problematic because they can mimic your astrophysical signals and sort of trick your network into thinking you're detecting a signal. So what we do is we identify these in our background strain, and during the training process, we'll oversample these so that the network can see enough samples to learn. And then in the bottom here, we do some standard time series manipulations like reversal and inversion that effectively give us a 4x increase in the amount of noise that we see. We also do some data augmentations for signals. So at the top here, I'm illustrating what we do with our waveforms. So we'll take intrinsic waveforms. So waveforms that are generated just from the intrinsic parameters like masses and spins, and we'll project those with randomly sampled extrinsic parameters like sky localization and distance. And this, again, allows us to sort of leverage a larger effective signal data set from some fixed set of intrinsic waveforms. In these bottom two rows, I'm sort of illustrating a strategy that we use to encode our knowledge of coincidence and coherence. So for signals, we expect between all the interferometers, coincidence and coherence. So in this middle row, what we'll do is we'll zero out one of the waveform strains, inject it into the data, and label that as noise. And this basically teaches the network that we expect in both interferometers at the same time to see excursions from the Gaussian noise. And then in the bottom here, we'll do an augmentation strategy where we will take one of the waveforms in an interferometer, swap that out with a waveform from a different template. And this sort of encodes our knowledge of coherence. So, it's not just enough that you have a lot of excursions in both interferometers, but you need the same morphology in the time frequency space for both interferometers. So once we have a trained model, a standard performance metric that's used for basically all gravitational wave searches is a sensitive volume. So the idea here is you measure the effective volume that your search is sensitive to at some fixed false alarm rate, given some population distribution of sources. So you're trying to calculate this integral on the right, where phi is your population and epsilon is your search efficiency. Yeah, so this is typically done with Monte Carlo integration because this integral is pretty complicated to calculate analytically. So what this ends up looking like is you'll inject a bunch of sources from your population phi uniformly in volume into your data, run your network over the stream of data, recover your injections, analyzed a whole bunch of background to be able to assign false alarm rates to those recovered injections and calculate the sensitive volume. So in this plot here, what you're seeing is false alarm rate, a plot of false alarm rate versus sensitive distance or sensitive volume. And this black curve is the result from the injected distribution, but we also perform a strategy where you can basically measure the sensitive volume for a variety of different distributions by only injecting one distribution and sort of reweighting those samples with important sampling. So it allows us to save on computation by only having to analyze one injection set. So Alec gave a brief overview of this distributed inference application that we've developed over the past couple of months. But you know, we have to analyze months to years of background to be able to assign high confidence error detections. And this can be problematic if you're, you know, only analyzing your data with a single GPU or CPU. So we've leveraged NVIDIA's Triton inference server to basically scale up the amount of GPUs we can use and sort of parallelize the inference of all these segments across a multitude of GPUs. And this, yeah, we've seen huge improvements. And this application has been showing linear scaling with the number of GPUs. So we're pretty confident we can scale this up quite easily. So looking forward for A-Frame, we're pretty excited about having an online deployment. We're in the middle of 04. It'd be great to be the first production level machine learning based detection algorithm in the Lego Kaggle collaboration. In the short term, scaling up the quantity of background data that we use. And then it would be awesome to be able to do end-to-end analysis of previous observing runs and compare with the standard match filtering pipelines that the collaboration uses. And then if you want to talk details, I have a poster later today. Okay, second part of the talk, I'll be discussing a different project where we are aiming to do parameter estimation of unmodeled gravitational wave sources with machine learning. And the sort of motivation here is that we want to be able to inform electromagnetic follow-up very rapidly, and machine learning can offer rapid inference times. So the sort of sources that we're tackling here are a little bit different than the compact binary coalescences that I was discussing in the previous talk, in the sense that we don't have well-modeled templates. So the goal here is to be able to do sky localization and parameter estimation for a generic signal where we don't really have good astrophysical models. A couple examples are core collapse supernova and neutron song glitches. The modeling is just not as good as for compact binaries. So what you end up doing is you use some sort of basis of minimal uncertainty wavelets and decompose your data and sort of search for coherent power between multiple detectors. So in this study, we use sine Gaussians, which are described by 5 or so intrinsic parameters. So they're quite simple compared to the 15-dimensional parameter space of CBZs. So the paradigm we've adopted to tackle this problem is simulation-based inference. So the Bayesian algorithms that we use typically in gravitational wave physics are quite slow, especially for the purposes of doing electromagnetic follow-up. So we sort of flip the Bayesian problem on its head. Instead of doing sort of nested sampling in MCMC, we have to evaluate exponential likelihoods. We'll simulate data from the likelihood and then train a neural network to approximate the posterior. And so we've been using normalizing flows where you essentially map some simple distribution to a more complex distribution. And then you can, via determinants and Jacobians, you can, sample from your simple distribution, pass it through your network, and get posterior samples. So here are some results. We recently got some good results on this model trained on sine Gaussians. So at the top, you can see a couple of sky maps from sine Gaussian injections produced by our model. The red cross, which is probably kind of small, but it's the true location, and we're recovering it quite well. On the bottom left is a probability plot where we sort of did a larger scale study of 1,000 injections, and we're essentially trying to make sure that our algorithm is not biased, and the diagonal line shows it's not biased. And then on the bottom right is an example posterior of an injection. We recover the parameters quite well. So looking forward, we want to be able to validate this model on actual astrophysical waveforms. So far, we've only been studying the response to these sine Gaussians, but being able to validate that our model generalizes well to compact binaries or other simulations is pretty critical. There's some work being done to exploit some symmetries for faster training convergence and just better performance in general. And we have a paper in prep. And yeah, if you have any other questions about this, see Deep Chatterjee's poster as well later today. And yep.
All right. Hi, everybody. My name is Erik, and I'm going to be presenting on anomaly detection. So kind of in a similar vein to what you just heard, we are calling our algorithm Guac or Guac. We haven't decided on the naming scheme yet, but basically, okay, so the bread and butter of LIGO is going to be your binary mergers. They have this down really well. And of course, we're even improving our pipelines with machine learning algorithms. And, you know, binary mergers are well modeled. And so we kind of know what black hole mergers are going to look like. We know what neutron star mergers are going to look like. And our LIGO detector is producing a one-dimensional time series for us to read out. The problem becomes when you have waveforms that are too complicated to model, or they're computationally prohibitive to model. So these are going to be your anomalies. So our match filter pipelines in LIGO can detect binaries, black hole mergers, neutron star mergers, black hole neutron star mergers, but there's certain anomalous signals that you just can't simulate or that are stochastic in nature, such as your core collapse supernovas, neutron star glitches, cosmic strings, neutron stars collapsing to black holes, different processes like this. It's just going to be way too difficult with the match filtering pipeline from LIGO to actually, you know, detect something like this. So that's where anomaly detection kind of comes in. And so the LIGO data set is going to be real non-trivial. You're going to have a bunch of noise on top of your signals. And then you're going to have glitches that are also approximating different types of signals that you're looking for. So we have to take all of this into account when we're building our algorithms. And so what we're trying to do is kind of take some unsupervised learning approach to the problem, where basically you have, you know, your typical autoencoder, and you have a reconstruction loss with your input and your reconstructed data. And then you take some threshold above, you know, some reconstruction loss of your output, and you trigger on some threshold, and you hopefully identify some event when your autoencoder fails to reconstruct your data. And so what we want to do is kind of generalize this for different types of anomalies within LIGO. And so this is where the quasi-anomalous knowledge kind of scheme comes in. And so it's called QUAC. And so basically what you do with QUAC is you make an axis for your background loss and your signal loss. Look on the left here. And then you make some kind of selection in this region to select for some hypothetical signal that kind of approximates the true signal. And then you can generalize this to, you know, 3 dimensions or really n dimensions. And so what we're kind of going to be looking for is like core collapse supernova in this QUAC space. And so, you know, the QUAC space is kind of in the high energy physics regime. And so we changed the QUAC to GUAC or GUAC, to, you know, just to make it our own. And so we have 4 classes for our GUAC algorithm. We train on binary black holes, sine Gaussians, backgrounds, and glitches for LIGO. And so we make these 4-dimensional spaces, embedded spaces, and then we look for different types of anomalies in the embedded spaces. And basically, specific regions of the GUAC space should correspond to different types of events. And so we have here, I have animated kind of a binary black hole merger and a sine Gaussian injection. And as you can see, on the binary black hole merger, when the merger actually happens, the point in space that you're at shoots over to this blue region, meaning that you're detecting a black hole. And similarly for the sine Gaussian injections, you shoot over to this red region here in the bottom. And so, you know, hopefully we can use this to detect supernova, other types of anomalies. We are validating on supernova and white noise bursts right now. And so, you know, this is kind of what a supernova looks like. It's approximated by sine Gaussians. And so I guess to finish up here, we have some qualitative results on anomaly detection. We're able to detect white noise bursts and supernova at a specific SNR, at a specific false alarm rate. And so if you want, more specifics, I'm presenting a poster later today. But basically, we're able to detect kind of mid-range SNR anomalies at a pretty low false alarm rate. And so it's going to be interesting to implement this in real time or for just the LIGO run 3 data that has already been collected. Yeah, I think that rounds out our research group. Thank you very much.
Thank you. We're a bit low on time, but we might have time for one question if anyone has one. Yeah. Just give me time to walk over here.
Thank you. Awesome presentation. I had a quick question about the quasi-anomalous, like quack space. So are you making kind of like augmentations to certain features of known anomalies in order to make these quasi-anomalies and to see if there's like some invariance?
So the way you build the space is you're going to want the axes of the space to be, known signals or backgrounds. And then you search for different regions of the space that you basically decompose an event into, its components of signal and background. And the way that you look for something new is just identifying regions in the space that you can, search for different anomalies. You don't necessarily make kind of any types of augmentations like you're talking about, but that could be an interesting avenue to explore for sure.
Thank you.
Thank you very much. Let's thank them again. Yes. Yeah. Just put the 3 presentations. So next we will have Josh Peterson presenting on behalf of Kael Hanson's group from the University of Wisconsin.
Can everyone hear me? I hope. Okay. So hello everyone. I'm not Benedict Radel. I'm Josh Peterson. And I'll be kind of giving an overview of the ML applications that we have in the IceCube collaboration, as well as some ML projects that are ongoing. And I guess just as a disclaimer, much of the projects I'm going to talk about, I'm not directly involved with, so answering questions may be interesting. So we'll see. So what is IceCube? So the IceCube Neutrino Observatory is a neutrino telescope that is located at the South Pole. It's essentially 86 strings, which have been instrumented with digital optical modules that have been embedded deep into the Antarctic ice. And this detector, its primary goal and purpose was for neutrino astronomy. So basically finding the sources of high energy neutrinos, astrophysical neutrinos. But as a detector, it actually has a lot of science topics that it can address other than just multi-messenger astronomy. And it also covers a very wide range of energies. So at MEV energies, we can look at the dark noise rate of our DOMs collectively to look for core cloud supernova. At lower energies like GeV, TV energies, we can analyze the atmospheric neutrino flux
to look at beyond the standard model physics and neutrino oscillation physics. And at higher energies, we can also do high energy neutrino astronomy. Ultimately, what this means is that we have a lot of data that needs to be processed, and they need to be processed in different ways depending on our science goals. It also means that we have a lot of different simulation that needs to be generated to help facilitate these science goals as well. Thank you. Okay, so in terms of multi-messenger astrophysics, why do we care about neutrinos? So there is a portion of our universe that is basically opaque with traditional astronomy. And so if we want to probe those regions of the universe, then we're going to have to use messengers that don't or that can penetrate those opaque regions. And there's a couple messengers that we can use. We already saw some information about gravitational waves, and neutrinos are also a good candidate for this as well. So how does this all work? Essentially, when a neutrino undergoes a deep inelastic scattering in the Antarctic ice, it's going to produce charged secondary particles. And when those charged secondary particles travel faster than the speed of light in the ice, it will produce Cherenkov radiation, which you can think of as basically the light equivalent of a sonic boom. So you get this directed cone of blue light. And all our digital optical modules are in that ice just looking for that Cherenkov radiation. And from that photon information, we can extract all of our important analysis variables like pointing direction and energy and stuff like that. So that was the ice cube detector. In the near future, there's going to be 2 expansions to Ice Cube. The first one, which is coming up literally, I think next year is drilling for this, is the Ice Cube upgrade. And so essentially, the Ice Cube upgrade is going to be installation of a few strings near the center of the detector. They're going to be more compactly spaced than the other strings, and they will be more densely instrumented with digital optical modules, and will also be switching from single PMT modules to multi-PMT modules. And the motivation for this upgrade is to push the energy threshold of the detector down so that we can do interesting studies like determining the neutrino mass ordering or doing Earth tomography with oscillations, cool stuff like that. And then later on, we will have Ice Cube Gen 2. And so essentially Ice Cube Gen 2, what will happen is we will put in a bunch of strings that are further apart. And the idea of this is to increase the energy threshold of the detector. So here we have our, in red is our detector currently, and then blue here is the instrumented volume that's planned for Gen 2. And the reason I bring this up is because what this essentially means is that we're going to have a lot more data that we're going to have to process, and again, we'll have a lot more simulation we'll have to run, etc. So processing this data efficiently is going to be very important. Okay, so what does our data actually look like? So the data in Ice Cube, you can essentially think of it as a time evolving point cloud, or you can think of it as a 3-dimensional movie. So here's some examples of events here. These black lines are strings, and each of these blobs is essentially a DOM that detected a photon, at least one photon hit. The size of these blobs represent the number of photons that interacted with this particular digital optical module, and then the color represents a relative time with each other. Now, in Ice Cube, there's a few typical morphologies that we tend to see. So if we have a muon neutrino that interacts in the ice, it will produce a high energy and it undergoes a charge current interaction. It will produce a high energy muon with high penetrating power, and that will just leave a long track of light, and hence we call it a track. Almost everything else we see is this cascade here. So when you have a deep inelastic scattering, you're going to have a hadronic cascade of charged particles, and so that will produce this more spherical feature. At higher energies, there's a chance that you can have a tau neutrino that undergoes a hadronic, a deep inelastic scattering, produces a hadronic cascade, and then the tau lepton can travel a significant distance before decaying, and then it decays and produces another hadronic cascade. And each of these different morphologies are good for different things. So for astronomy, these tracks are really good because you can reconstruct the pointing direction really well. But this muon can escape the detector, and so it's not as easy to reconstruct energy. Whereas with these cascades, it's significantly harder to determine the pointing direction that the neutrino came from with these events, but you can capture the whole event a lot easier in the detector, and so you can get good energy reconstruction. So we mentioned these different morphologies. So pretty much every analysis in IceCube is going to have to sort out these flavors in some way. And so what I've shown here are really nice examples, but there's some significant complications. So one example of a complication is at lower energies, we have less information. So here I show an example of a track, an example of cascade at 30 GeV. And as you can tell, it's really hard to distinguish between the two. So this is where machine learning applications can really help out. In addition, at higher energies, we can have catastrophic or stochastic energy losses due to bremsstrahlung. So here we have two events that in the simulation, they're injected at exactly the same angle, at exactly the same energy, but we see two different realizations. And one of our biggest systematic is the ice models that we use. So we're constantly upgrading our knowledge of the ice, and what ice model you use can have a pretty significant impact on how your events will actually look like in the simulation. So as an example, for how CNNs can help us with some of these classification tasks, there's an analysis that is fairly mature in IceCube in which we're looking for astrophysical tau neutrinos. These are especially difficult at lower energies because that tau lepton can't travel far enough to really separate the two hadronic cascades. And so you just get something that looks like a cascade. And if I ran just the standard maximum likelihood method on this, it would just come up as a cascade, more or less. However, we can look at the actual voltage waveforms that are produced in the DOMs. And the hope is that even though visually you can't really see it macroscopically as two separate cascades, you might be able to see it in the waveforms that are in the digital optical modules. And so what we've been able to do is use a convolutional neural network. And basically we construct these two-dimensional images where on one axis we have the digital optical module number. So this is essentially analogous to depth in the ice. And then the other axis is time, and we just plot this voltage waveform for every DOM. And then we can use this two-dimensional convolutional network to evaluate these things and look for these astrophysical tau neutrinos. So I mentioned the ice models before. So how we've been using these ice models is essentially we construct these photon tables that basically allow us to just look up if a neutrino interacts here and it undergoes a hadronic cascade, then what is the probability that I see this many photons in this DOM in the particular area of the detector? And as our ice models are becoming more advanced and more developed, these tables are becoming more unwieldy and harder to generate. And so there is an idea that, okay, instead of developing these tables, why don't we develop a generative CNN to learn this PDF? and this has additional benefits, like we're able to use gradient descent as a minimizer, which is pretty nice. And I think this is fairly mature at this point. And in the future, right now we have it for just like our standard analyses are available for standard analyses. The next step would be if we can incorporate this thing into multi-messenger astronomy, which I'll talk about later. So this is another example where neural networks can help us. So basically with IceCube, we're really sensitive towards the northern sky, and this is because basically we use the entire Earth as a shield for atmospheric background. However, there's a lot of sources that are really interesting in the southern hemisphere as well, and we would like to look at those. But there's some significant challenges with that. And obviously one of them is you don't have the Earth anymore to protect your detector. So now we have this huge atmospheric background that we have to deal with. And it turns out that you need to make pretty precise cuts to actually deal with this background. And it was found that these, if you want to make energy cuts with these track events, that's not going to be precise enough to deal with this background. And so it was found that if we want to really look at the southern sky, we're stuck with these cascade-like events, which have a poorer pointing resolution, but we can know the energy much more precisely, and so we can make those cuts that are necessary to really cut down on the background. And so recently, what we found was that boosted decision tree and CNN methods for reconstructing the direction of these cascade events were outperforming the standard maximum likelihood methods. And recently, maybe some of you have heard about this, because of these neural network-based methods, these machine learning-based methods, we were able to recently identify a third source of high-energy neutrinos, which is the galactic plane. So that was a very exciting recent result. We had a Kaggle competition recently, and this was just basically, I think I mentioned this in an earlier A3D3 workshop, but basically the idea was to allow the broader audience to try and develop algorithms for reconstructing neutrino pointing direction. So the results are in. It's very exciting. All the top 3 results are actually better than the models that we're ending up using. And another interesting thing is that the winning models tended to use transformer models. So we'll probably have to switch to that. I think this winning solution was a mix of transformers and GNNs. And that data is publicly available. So if you guys want to take a stab at it, you're not going to win any money anymore, but you can definitely go for it. Okay, so getting back to multi-messenger astronomy. As I mentioned before, if we really want a more rich understanding of the universe, then what we'll really have to do is, if we identify some kind of source or we see some kind of transient, we really want to look at it with as many messengers as possible. And as an example of kind of the importance for this kind of thing, the first high energy neutrino source, TXS 0506, this was found because of an optical follow-up. So basically, it's charted here. We sent out an alert for a neutrino that had a high probability of being astrophysical, and then all of these other experiments followed up, and they saw that, yeah, there's this transient flare-up that's corresponding to that direction. And so to actually accommodate this kind of regime where we're doing multi-messenger astronomy, you need a fast response to alerts, and that requires significant cyber infrastructure. So this is kind of the basics of how we do things now. So basically, neutrino comes in from some source in outer space. It interacts it here, and then we have some quick tests to just determine, is this likely astrophysical or not? And if it is, then we can send that alert data through an Iridium satellite up to the north, where then we can send out that alert to the to optical experiments that can look in the same direction. If there's anything interesting. So typically, when we want to do these fast reconstructions, we need to determine, okay, where did this neutrino come from, and what is the 90% contour from this. And typically what we do here is we break up the sky into different segments, and then you calculate the maximum likelihood for each of these segments. And this is actually pretty computationally efficient because you can calculate the likelihood for each of those different segments in the sky independently, or in parallel, basically, independently. So right now, we do this with just traditional methods. Is there a chance to actually incorporate ML? This is still somewhat an open question. The main issue is holding us back is essentially understanding the errors that are coming out of machine learning. And this is basically just because the errors that would come out of machine learning would be based on the simulations you use to train it. And if we don't fully rigorously understand these errors, we basically want to minimize the chance that we send out some alert like this, where the 90% contour has multiple sources, and then we just lead people astray to some source that isn't actually relevant or important. And so probably if we're going to incorporate neural networks, our best bet is to do something like I mentioned with the ICE models before, where you do some kind of hybrid with maximum likelihood and neural networks. Okay, so if that's one way to speed things up, what are some other ways to speed up this MMA infrastructure? Right now, it takes about 30 seconds to actually like go from detection to we're sending alerts out. And actually, the biggest computational sink is from this one process, waveform unfolding, which is basically just we have our voltage waveforms from the PMTs and we want to extract the photon information out of it. And currently, 30 to 50% of the CPU time at the South Pole is just dedicated to this. Unfolding. And so this is kind of a prime candidate for acceleration using different ML methods possibly, or just different things other than CPU like GPU or FPGA. So this is something that we're working on now, is just developing a simple algorithm for unfolding using machine learning. And we have some preliminary results where we literally we have a compact small MLP and we just scan it over the waveforms, and we've trained this MLP to just look for photon hits. And I won't go into too much detail because I have a poster presentation on this. So if you want to know more, you can just come ask me. But the initial results are actually looking really good. And so there's definitely room to improve on this and maybe use more sophisticated neural networks. And hopefully the plan is if we get this working well enough, then we can implement it on GPU and FPGA. And most ideally, if we get it working on FPGA and it's compact enough, then we can port this whole process into the digital optical modules in IceCube Gen 2 instead of having to send the voltage waveforms up to the surface to be processed by that CPU farm, basically. And then this is something that we're planning to do in the near future. We have this algorithm for unfolding where we basically take the typical response to a single photon of the PMTs, and then you just find the linear combination of these time-delayed SP response templates that reconstructs your waveform. And that gives you the photon information that you want to extract. We do this with the loss and Hanson non-negative least squares algorithm. And this is just an algorithm that's almost all linear algebra. So this is a prime candidate for being accelerated with GPU. So in the near future, we will port this to GPU, and then we can compare the ML method and the GPU method, just the straight implementation on GPU. That's it. I can try and answer questions.
We maybe have time for one question. Anyone? Yeah, go ahead.
Could you comment on why do you need a FPGA? Is a
Oh, FPGA.
latency requirement?
Why we want the unfolding on FPGA?
Yeah.
Yeah, so this is kind of like motivated by the fact that ultimately the most ideal situation is we port this unfolding process into the digital optical modules. And the hardware for the digital optical modules for Gen 2 is basically set in stone at this point. And so what's available on those digital optical modules is basically a number of FPGAs. And I think there might be a central microcontroller unit. So that's basically the only targets we have in DOMs. If we don't end up being able to port to FPGA, then we probably wouldn't be able to do that. And then GPU would probably be a more ideal candidate for acceleration.